Hello again, and welcome to our second lecture on developing the 6 trigonometric functions. Last time we defined these functions using a right triangle definition, and unfortunately we were restricted to acute angles. Well, today we'll have another way of defining the trig functions, equivalent to this previous definition, but it'll be valid for all possible angles, positive or negative. And in fact, we'll discover near the end of the lecture that we can consider these trigonometric functions as functions of a real variable, functions of real numbers, just like the exponential function and polynomial functions were functions of real numbers. So let's see how to do this. Let's see how to define the trigonometric functions for an arbitrary angle. Well, the setup is, consider an arbitrary angle theta, and here I've drawn one where theta actually is bigger than 90 degrees. And the terminal point I'm going to label with coordinates x, y, that's over there in the second quadrant, and the distance from that point to the origin is r, and by the Pythagorean theorem, that's equal to the square root of x squared plus y squared, which we're assuming is non-zero. So again, xy is the point on the terminal side of our angle. Okay, the definition of the trig functions is really quite simple. The sine is defined to be y over r. Back in the picture, it's the y coordinate divided by that radial distance to the origin. Cosine is defined to be x over r. And tangent is either sine over cosine or y over x. Same thing. And then you have the reciprocal functions. Cosecant is r over y, secant is r over x, and cotangent is x over y. Now you might notice something right away with these definitions. For some values of x and y, these functions are not defined. And we'll come up with some examples of that in a moment. But if y is 0 or if x is 0, they aren't defined. So that's a little kicker there that we have to worry about. Some textbooks, if you look at this definition in textbooks, they assume that distance r is always 1. It makes no difference. I'm assuming it's an arbitrary distance r, but if you want to use distance 1, that's fine. It simplifies some of the computations. The definition of these trig functions really only depends on the angle. Okay, good. The good news is this definition agrees with the previous lecture's definition using right triangles. You get exactly the same answers. I haven't defined some brand new functions. These are the same old trig functions that we've learned to love. Okay, let's do some computations with trig functions, with this new definition. Suppose our terminal point on our angle is the point -3, 4. So x is -3 and y is 4. Here I've drawn a picture of that. The angle actually ends up in the second quadrant, doesn't it? And the coordinates are -3, 4, and you can sort of see that the distance r back to the origin is going to be 5. -3 squared plus 4 squared adds up to 9 plus 16 or 25, and you square root it, you get 5. So we know now what x is, we know what y is, we know what r is. We can now figure out all the trig functions for this obtuse angle. Here we go. What's sine? The definition is y over r. So it's 4 over 5. How about cosine? This is kind of interesting, I think, because cosine x over r turns out to be negative because x is -3. So here's a case already where we have an answer that's negative. And tangent, of course, is y over x, so it's -4 over 3. Or if you want, you can get that by doing sine over cosine. Even though that cosine was negative, do notice that the absolute value of that value of cosine, the absolute value, is still less than 1. The values of sine and cosine are always in a sandwich between -1 and 1. They might be negative, that's the point. Okay, these trig values can be positive or negative depending on which quadrant the angle is located. If you're in quadrant 1, like we were in the previous lecture, sine's always positive, cosine's always positive, and tangent's always positive. And that's sort of the most comfortable situation. We just saw an example where our angle was in quadrant 2, and we noticed that sine was still positive, but cosine turned out to be negative, as did tangent. Going down to quadrant 3, sine and cosine are both negative, but lo and behold, their quotient, sine over cosine, which is tangent, that'll be positive. And finally, in quadrant 4, sine is negative, cosine's positive, tangent again is negative. So depending on the quadrant, the sign, S-I-G-N, of sine might be plus or minus. Kind of confusing when you have the sign of sine. Okay, let's do an example. Suppose the sine of some angle is minus 2/3, and suppose its tangent is positive. Find the cosine, and say find the cotangent of this angle. So we don't know what the angle is, but we know its sine. Its sine is minus 2/3, and we've also given an added fact. The tangent is positive. Well, ask yourself the following question, first of all. Where is this angle located? If your sine is negative and your tangent is positive, where are you? Where's the angle? Oh, we're actually in quadrant 3. If you remember, in quadrant 3, the y's are negative, but the tangent is positive down there. That's going to help our computations. So let's go ahead and answer the question. We know that sine theta is y over r, and we're given that it's minus 2/3, so we might as well assume that y is, say, minus 2 and r is 3. Remember, r always has to be positive, so y is forced to be negative. Now let's find x. Well, Pythagorean theorem, r equals square root of x squared plus y squared, so r squared is x squared plus y squared. We know what y squared is. Y is minus 2, so its square is 4, and we have x squared is 9 minus 4 equals 5. So what's x? Careful here. X is going to be negative, isn't it? We're in quadrant 3. X is going to be negative, so it's negative the square root of 5. That's the x value. And now we can finish off the problem. Once we know y and x, everything else is pretty easy. Cosine is x over r minus square root of 5 over 3, and cotangent is x over y, which is minus square root of 5 over minus 2, which is root 5 over 2. Notice cotangent came out to be positive, didn't it? Cotangent is the reciprocal of tangent. So if tangent is positive, so's cotangent. And of course, you could do decimal approximations of these as well. Now, some angles occur all the time. Last lecture, we noticed the 30, 60, 90 right triangle, and we computed 45 degrees. Let me point out some other angles that are even simpler. Consider the following picture. Here I've drawn 4 points in the plane. One of them is 1, 0, and then 0, 1, and then minus 1, 0, and 0, minus 1. The point 1, 0 corresponds to the angle 0. And 0, 1 would be the right angle, pi over 2, or 90 degrees. And then you go over to minus 1, 0. That's an angle of pi radians, or 180 degrees. And finally, 3 pi over 2 is down there at the bottom. Well, the sine, cosine, and tangent of these 4 points occur all the time. Let's look at what those values are. What's the sine of 0? Well, it'll be the y value divided by r. Well, r is 1 here, isn't it? I've chosen this to be unit distance. So sine of 0 is 0, the y value. What's cosine of 0? It's the x value, 1. So sine of 0 is 0, cosine of 0 is 1. Let's swing over to pi over 2. What is sine of pi over 2? Well, that's going to be 1. That's the y value, but cosine is 0 there, isn't it? And you can keep going. You can calculate sine and cosine for these 4 crucial values. Let me point out something really interesting, though. What's the tangent of 0? Well, tangent is y over x, so it's nothing more than 0 divided by 1. So the tangent of 0 is 0. But what about the tangent of pi over 2? Well, pi over 2 is up there at the top. It's y over x, 1 over 0, division by 0. Tangent pi over 2 is not defined, is it? And many of the trig functions, well, 4 of them, tangent, cotangent, cosecant, and secant, suffer from this problem of not having a full domain of real numbers. They have some of these bad points, like pi over 2 for the tangent function. And we'll see more of this later. Okay. It's pretty hard to calculate trig values for arbitrary angles. If I were to say to you, what's the sine and cosine of 300 degrees? You sort of go, well, I don't know, how do I do that, etc. Let me show you one way of reducing the problem of calculating the trig values of arbitrary angles to the problem of computing trig values of acute angles. And we're pretty good at acute angles, small angles, those angles in the first quadrant. We're pretty good at that. The previous lecture permitted us to calculate those trig values. So for an arbitrary angle, we will reduce the problem to that of finding the trig values of an associated acute angle. Let me show you how this works. It's slightly complicated, and it's a technique that many students prefer. I'll be honest with you, I probably don't do it this way myself, but I probably should. So here's how this works. Let theta be an arbitrary angle in standard position. Its reference angle is an acute angle, which I'll call, say, theta prime. So the reference angle is called theta prime, and it's formed by the terminal side of theta and the horizontal axis. A picture will explain this much better than the words. Here I've drawn an arbitrary angle theta. It happens to be in the second quadrant. The corresponding reference angle is the acute angle that line forms with the x-axis, and I've drawn it there, and that's an acute angle, isn't it? Let's do some examples of this. 300 degrees. What's its reference angle? What's its corresponding acute angle? Well, here's a picture. There's 300 degrees. It's all the way around to the fourth quadrant. And if you add 60 degrees to it, you get 360 degrees, and you make a complete circle. So the corresponding acute angle would be 60 degrees here. Okay, that's the angle it makes with the x-axis. Let's try another one, because this is a little tricky, I admit. What's the reference angle for minus 135 degrees? Let me ask you another question right away. Do you know the sine and cosine of minus 135 degrees? I sure don't. But with this technique of reference angles, you'll be able to find out. So here we go. Let's find the reference angle for minus 135 degrees. Well, first of all, it's coterminal with 225. How do I get that? Add 360, meaning go around the circle one more time, and you end up at 360 minus 135 equals 225. So 225 is coterminal with minus 135. What's the reference angle? Well, take off 180 and you get 45 degrees. Again, a picture is worth 1,000 words here. I've drawn here minus 135 degrees. It's a negative angle, and it's over there in the third quadrant. It's coterminal with 225, which I've also indicated. And finally, that angle makes an acute angle of 45 degrees with the x-axis. So the reference angle is 45 degrees. All right, great. Can we find reference angles? I think we can now. Let's go the final step. What do we do with these reference angles? Well, to find the value of a trigonometric function of any angle theta, here's what you do. You find the reference angle. First find the reference angle, and then determine the trig value, the function value, associated with that reference angle, with that theta prime. Now, that's not quite the right answer. You then have to make a study of what quadrant you're in, because you might have to put a plus sign or a minus sign in front of it. It might be negative. You'll know the absolute value of the answer, but you might have to affix a minus sign depending on what quadrant. Let me illustrate that with that same problem we saw earlier, 300 degrees. What's the sine of 300 degrees? Again, I think I have to admit, I wouldn't know how to find that without knowing these reference angle techniques. My calculator could do it, I suppose, but doing it by hand, let's step through it. Well, we saw earlier that the reference angle was 60 degrees. Okay, that was the reference angle for 300 degrees. Now, we're pretty comfortable with 60-degree angles. We studied the 30, 60, 90 right triangle last lecture, and we discovered that the sine of 60 degrees is square root of 3 over 2. Okay, that was one of those important triangles and an important angle, 60 degrees. The sine is square root of 3 over 2. Is that the sine of 300? Where is 300? It's in the fourth quadrant, so it's going to be negative, isn't it? So the final answer is minus square root of 3 over 2. You have to stick that minus sign in there because an analysis of the quadrants tells you that sine is negative down there. All right, tough going, I admit. But the bottom line is, if you're comfortable with angles in the first quadrant, you can now find the trigonometric values for all angles that are fairly simple, like 300. Let me show you a table that we perhaps should savor together. It consists of common angles between 0 and 270 degrees. In fact, the most important part is between 0 and 90 degrees. These are angles that occur all the time when you're studying trigonometry. And in this table, we've listed in the first row the angle in degrees, in the second row the angle in radians, the corresponding angle, or the conversion to radians, and then we've computed the sine, the cosine, and the tangent of that angle. Let me just point out a few items in this table, and I'll let you kind of look at it later on. This table will be in the appendix of our workbook, and it's worth kind of looking it over every so often and pointing things out. For instance, look at 45 degrees. That's pi over 4 radians. And last lecture, we computed the sine and the cosine. They were both square root of 2 over 2, and the tangent turned out to be 1. Or look at 90 degrees, or pi over 2 radians. The sine is 1, the cosine is 0, and remember, tangent's undefined there, because tangent is sine divided by cosine, and you can't divide by 0 in mathematics. So that's a worthy table to kind of look over in your free time every so often. In fact, a lot of times when students are taking tests, I've noticed this, they'll walk into the test and they'll sit down and they'll write on a piece of paper all these trig values, sort of to have them in front of them. They've kind of memorized them and they run into the test, write them all down, and then start taking the test. And when they need to know the cosine of 30, they look over to the table they just wrote down. Kind of neat. Sure, why not? Okay. Let's do some more examples and see how these reference angles work, etc. Let's compute the cosecant of 11 pi over 4. At first glance, this problem looks, ouch, pretty hard. Let's see how we might do it. Well, first of all, 11 pi over 4 is coterminal with 3 pi over 4. How did I get that? Well, I subtracted 2 pi, which is 8 pi over 4, and 11 minus 8 is 3. So it's 3 pi over 4. Those are coterminal now. Okay. Now, what's the reference angle for 3 pi over 4? It's the corresponding acute angle pi over 4. So now we're getting somewhere. Pi over 4 I'm comfortable with. So cosecant of 11 pi over 4 will be cosecant of 3 pi over 4 because those are coterminal. Cosecant is 1 over sine, so it's 1 over sine 3 pi over 4. And now I say, well, wait a minute, the reference angle is pi over 4, so it's square root of 2 over 2. Is it plus or minus? What is the sign, S-I-G-N, that I have to put in front? Well, where is this angle? Where is 3 pi over 4? Or if you want, 11 pi over 4. Ah, it's in quadrant 2. 0, pi over 4, pi over 2, which is 2 pi over 4, 3 pi over 4. It's in quadrant 2. So I use a plus sign because the y-coordinate is positive there. And so it's 1 over sine 3 pi over 4, 1 over square root of 2 over 2. Flip up the fraction, you get 2 over square root of 2. Hard going, wasn't it? Non-trivial problem. And as we pointed out a number of times, you might see this written different ways. We just wrote it as 2 over square root of 2, but your teacher might say, oh, you should always rationalize denominators, so you would multiply by square root of 2 divided by square root of 2, and then get 2 square roots of 2 over 2. The 2's cancel, and your answer is square root of 2. A better looking answer. Kind of nice. Notice something here. Just occurred to me. Remember I said that sine and cosine are always sandwiched between -1 and 1? What does that mean about their reciprocal functions, cosecant and secant? Oh, they're going to be either bigger than or equal to 1 or less than or equal to -1. And notice that the square root of 2 is bigger than 1. Nice. Okay. How could you check your answer? You could use a calculator. Here's the answer I got. I got cosecant 11 pi over 4. The way I did it, on my calculator, I punched in 1 divided by sine of 11 pi over 4, and I got 1.414 ... some more numbers. And then I recognized that, oh, that's the square root of 2. Wow. And I was, of course, smart enough to use the correct mode, to use radian mode for that calculation. Okay. Let's do another example. Suppose you're given that the sine of theta is a third. The sine of theta is a third, and your angle's in quadrant 2. Can you find the cosine and the tangent? So sine is a third. What's cosine and what's tangent? Well, let's do it. And we're going to use our fundamental identity one more time here. So sine theta is 1/3, and that identity, one of my tattoos, sine squared theta plus cosine squared theta equals 1. Plug into that, we know what sine theta is a third, so 1/3 squared plus cosine squared equals 1. Solving for cosine squared, 1 minus 1/9, 1/3 squared is 1/9, that equals 8/9. So cosine squared is 8/9. What's cosine? Careful now. We're in quadrant 2. Cosine positive or negative there? Oh yeah, cosine's negative there in quadrant 2. So I take the square root and I put a minus sign in front of it. So cosine theta is minus square root of 8 over 3. And then you can actually simplify square root of 8 to be 2 square roots of 2, all divided by 3, with that minus sign in front because we're in quadrant 2. And now the rest is easy. Once you know sine and cosine, you know tangent. It's just sine over cosine, 1/3 divided by minus 2 square roots of 2 divided by 3. The 3's cancel, minus 1 over 2 root 2. And then you can rationalize that denominator if you so choose. And if you do, you'll get minus root 2 over 4. All right, we've arrived at an important point in the course here. We're going to step up our maturity level a little bit. We've been computing a lot of trig values, and I sort of think that's a little mundane and kind of, it's some heavy lifting there, a lot of calculations, calculations that calculators can do, thank goodness, and verify our results. Now we're going to look at these trig functions a little bit differently. Okay, and I'm going to specialize to sine and cosine right now. We've been looking at the sine and cosine of an arbitrary angle theta. And theta can be positive, negative, whatever. And it can be in radian measure or degree measure. Let's use radian measure for the moment. The domain of this, theta, is allowed to be any real number you want. So the domain of this sine function or this cosine function is all real numbers. Something else we've observed, whatever angle you have, the sine or the cosine is in between a sandwich between -1 and 1. The output never gets too big. It's always between -1 and 1. So the domain is all real numbers. The range is the interval -1 to 1. Here's a further fact about this sine function and this cosine function. If you have sine of an angle, and then you add 2 pi to that angle, you come back to the same point, don't you? They're coterminal. So the sine of theta equals the sine of theta plus 2 pi. I can do even better. The sine of theta equals the sine of theta plus 2n pi, where n is any integer. I can go around 5 times and come back to the same point. Mathematicians call that periodicity. The function sine is periodic with period 2 pi. It repeats itself. The sine of 45 degrees will be the same as if I go around all the way and end up at that same spot. Okay. So we've got this function, the sine function or the cosine function. We know its domain. We know its range. We could draw a picture of it, couldn't we? We could graph it. For every value of theta, graph sine theta. Now, here's one of the awkwardnesses, though. We got to be a little more mature here. When we graph in the xy coordinate system, don't we? But we've been using theta as our independent variable. We're going to switch gears now. We're now going to use x to indicate the angle. Uh-oh. This is not the same x we were using as the point xy. We're changing variables completely here. So imagine now the function sine x, where x is an angle. Okay, x is an angle. And the output will be the value of sine x at x, and that'll be called, say, y. So we'll have y equals sine x. That's a new function. F of x equals sine x. Just like we had the exponential function f of x equals e to the x, we now have developed a function called the sine function. F of x equals sine x. And for every x value, you compute its sine the way we've been doing, except we've been using the letter theta. Forget about theta now. We're now going to use x as our variable, our independent variable. And the output will always be between -1 and 1. And for the sine function, we're allowed to put in any x we want because it's valid for any real number. All right, that's a big jump, I think. In fact, historically, that was a big jump in the development of trigonometry. Initially, it was used for things like measuring the height of a tree. Well, now we've got functions. Wow, we've taken a quantum leap, I think, in depth now with developing the trigonometric functions. Let me show you a quick application of just how this might work in a real-life situation. Suppose you have a spring hanging from the ceiling and it bounces up and down. It's got a little bob here, a little boing, 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 boing like this. You can model that spring with a trigonometric function because the movement is periodic. It just goes back and forth over and over again, much like your heart beats in a pattern like that, or a wave goes in a pattern. And let's suppose our spring is modeled by the function 2 sine t. Whoa, now I'm using t instead of x. We went from theta to x to t, but I like t because it's time in this model. Well, don't panic here. All I'm really saying is, for a given t value, you can compute the position y. For example, when t is 0, it's 2 sine 0 or 0. It's at equilibrium. And then when time is pi over 2, you'll have 2 sine pi over 2. Sine of pi over 2 is 1, and so it's up to position 2. And then at time pi, it's back to equilibrium because sine of pi is 0. And then it goes down, and it goes up, and you can plot the position of this spring by using this trigonometric model. All right, great. We've done a lot today, I think. We've developed the trigonometric functions for arbitrary angles. We worked really hard to calculate the values of trigonometric functions using those reference angles. I'm the first to admit that's a non-trivial skill. The workbook has some nice practice problems where you'll be invited to calculate trigonometric functions for arbitrary angles. Next time, we're going to continue this study of the sine and cosine functions as functions of a real variable. We'll see the graph of the sine function and that of the cosine function. We'll use the periodicity that it repeats itself. And to complicate things a little bit, we'll take some of those graphs and stretch them and move them a little bit to see some other periodic functions. Okay, so thank you very much, and I'll see you next time when we study the sine and cosine in more depth.